Hi there. So let's suppose you go to school one morning and you find out there's a quiz and you haven't studied for it at all. You don't know the first thing about this and you've got to resort to random guessing on a multiple choice quiz. What are the probabilities that you'll pass? Well, you can actually calculate those probabilities with just a little bit of information and something called the binomial distribution. And in this next set of slides, I'm going to show you how it works. So the binomial distribution is just like any other probability distribution. It relates certain probabilities to certain events happening. The binomial distribution really is related to coin flips of how many coin flips might come up heads out of 10 flips or something like that. So if you have a 10 question quiz, you could figure out what's the probability that you would, flip a coin and answer correctly 6 of those 10 times. So it doesn't have to be coins. It can be quiz questions. It can be basically anything that is binary. And you can think of a lot of things as being binary. Whether you answer a question correctly is a yes or no question, maybe on a multiple choice. Whether if you're doing epidemiology, whether a person has a disease or not is actually a binary thing, or whether the person gets cured or not could be considered binary. Alive or dead could be binary. So this binomial distribution can cover a whole lot of different phenomena that we might want to learn about. What's more is that unlike coin flips, these probabilities don't have to be 50-50. So it could be a very biased coin, and we could still calculate the probabilities of success. So now with that disclaimer out of the way, let's figure out how this works. Let's start out with a simple coin flipping example. We're going to flip 3 coins, and we want to know what's the probability that 2 out of the 3 come up heads. We don't care the order, just that 2 out of the 3 come up heads. And just to keep things a little interesting, let's say that the probability of any one coin coming up heads is now 60%. So it's no longer a fair 50-50 type coin. It's now a 60-40 biased coin. So the way to address this is to start by drawing a probability tree of all the different possible outcomes we could have. So let's get started. We could have our first flip, and that could come up a heads, or it could come up tails. So that's our first 2 possible options for our coin flip. And along our branches, let's put the probabilities. So we said that the probability of a head was 60% and the probability of a tails was 40%. Okay, so that's for our first coin flip. Now what about our second coin flip? Well, if the first one came up heads, our second one could come up either heads or tails. Again, with probabilities 60 and 40. And likewise, if our first one came up tails, doesn't matter. The second one could come up heads or tails. And these are all independent coin flips, so it's not like the probabilities of a head change. We still have 60 and 40. Okay, so now we flipped our coin twice. What about our third flip? Well, we could have heads and tails again, with probabilities 60 and 40. And likewise for all of our different options. So I'm going to do that real quick. Now that my table is drawn, let's see what all the different possible outcomes we might have had. We could have started out with a heads, followed by heads, followed by another heads. So we could have had 3 heads. We could have had heads, heads, tails. We could have had heads, tails, heads. and so forth. Let me fill in the table. So we've now listed all of our possible outcomes. What are the probabilities that each one of these things had happened? Well, let's start with this top case. The probability of 3 heads. Well, each coin had the probability of coming up heads 60%. So the probability of 3 heads would then be 60% times 60% times 60%. So let's write that down. The probability of heads, heads, heads is 0.60 times 60 times 60. That's 0.60 cubed. What about heads, heads, tails? Well, the first coin had a probability of coming up heads 60. Then we would have had to have another 60. So heads and tails. The use of the word "and" there should tell you that we should be using a multiplication rule. So 60% times 60% times 40%. So let's write that down. Heads, heads, tails. That's 60 squared times 40 to the 1, right? 60 times 60 times 40. Let's do another one together. Heads, tails, heads. Well, that was 60% times 40% times 60%. So we can just group them like this. And so forth. Let me fill in the rest of the table, then we'll circle back. Just as a little addendum, let's include here a 40% raised to the power 0. Anything raised to the power 0 is just a 1, and we can always multiply by 1. So this is kind of a benign addition. Now our question asked, what's the probability that we had drawn 2 heads out of the 3? So let's see, where did those happen? We got 2 heads here with heads, heads, tails. We had 2 heads here with heads, tails, heads. And we had it here with tails, heads, heads. Now the question asks, what's the probability that we had gotten heads? There's 3 different ways of doing this. Heads, heads, tails, tails, heads, and tails, heads, heads. So the probability of getting 3 heads really could have happened one of 3 different ways. It could have been this way, or it could have been heads, tails, heads, or it could have been this way. Any one of those 3 ways works. So since I said the word "or" there, that should be your tip-off that we're looking at an addition rule. So we just need to add up those probabilities. Incidentally, these probabilities are all 60% squared times 40% to the power 1. So we have 60% squared, 40% raised to the power 1. We have that 1 time, we have it a 2nd time, and we have it a 3rd time. 1 for each of these occurrences. They're all the same probability. So we could just say 3 times 60% squared times 40% to the 1. So we can key that into a calculator and get the result. The precise numeric result, though, isn't nearly as important as what this exercise can show us about what a more general formula might be. So let's stare at this formula for a little while and see if we can make sense out of it. It's much better to make sense out of a formula than just mechanistically plugging in numbers. The first thing to think about, let's work inside out. So 60% was our probability of success. We had 2 successes, so this is just probability of success in a single trial, but we need 2 of them, so we multiply 60 times 60, and we get our squared there. So it's the probability of a success raised to the number of successes. That was the 60 squared. Now, if 60% is your probability of success, then you must be failing 40% of the time. So that 40% really is 1 minus the probability of success. Now, how many failures did we have? Well, if we had 3 trials and 2 of them were successes, then 1 of them must have been a failure. So that 1 really was the number of failures. Now finally, what about this term here? Now it's hard to see because this was done as a very simple example, but that 3 really comes from all of the number of different ways that we could have chosen 2 numbers, 2 heads, out of 3 coin flips. Really, this was a combinatorial problem of adding up 3, choose 2. Now if you need a reminder on how to do combinatorial problems, just click on that link for a refresher. Now 3 choose 2 we know is 3 factorial divided by 2 factorial times 1 factorial. That just simplifies to 3. So that's what that is. It is the number of trials divided by the number of, not divided by, a number of trials choose number of successes. So let's just replace our specific formula with something a little bit more general. So really what we want is the number of trials, choose successes. That's our general formula. So let's practice using it. We'll do a very similar example to the last one. So here's our formula for the distribution of a binomial random variable. If we have n trials, so n is the number of trials, think of that as the number of coin flips, how many, what's the probability that we would have k successes? In our previous example, we considered a heads being a success. Doesn't have to be necessarily a good thing, it's just the thing that you're interested in. So if you wanted to know what's the probability out of 100 folks that you find somebody with cancer, you could call that the success, which is rather twisted, but it's rather arbitrary as well. We're just calling the thing we're interested in, that phenomenon, a success. Whether it's existentially good or bad, statisticians don't have such morals. So we can now answer all kinds of questions about the probability of, if we have binary events, but we give it up to, so many trials, how many of those are going to be successes? The catch here is that each of those trials has to be kind of like a coin flip. It doesn't have to be equal probability heads or tails, but the coin flips have to be independent of each other. So if for some reason the coin starts to get damaged in the flipping, then you can't really use the binomial theorem. Sometimes people try to use the binomial for analyzing free throws, but if you start thinking you've missed a whole bunch of free throws, then psychology kind of messes with your head, and then you're a lot more likely to start missing after a stretch of misses. So something like that isn't necessarily really modelable by the binomial theorem. At any rate, let's do just another example here, just for the sake of practice. Let's say that you're going to play 3 games, so kind of like before with 3 coin flips. The probability of winning a game is now 20%. What's the probability that you win 2 of the games? All right, so the number of games, n, that's 3. You want to know the probability that you win 2 of them, so successes is 2. Okay, so what's the probability of 2? Then we need the probability of success. So winning, the probability there is 20%. That happens 2 of the times, which means the 80% of the thing has to happen the remaining 1 of those times. So we can just key this into a calculator and get our result. Let's do that. And we get 0.096 or 9.6%. Okay, now I led off with what's the probability of random guessing on a quiz. Let's do that example right now. So you haven't studied for the quiz, and so you got to guess. The probability of a correct guess is 25%. Essentially, think of this as a multiple choice question. You have A, B, C, and D. So you got 4 answers. They all look good. You've got no idea. So the chances of getting 1 question correct is 25%. And what's the probability that you get a 6 out of 10? Right? We'll do that question first, then we'll do getting a 60% or better. What's the probability that we get exactly a 6 out of 10 on our quiz? Well, we can use the binomial theorem for this. Let's see how this works. So what is the probability that we get a 6? Well, we've got 10 questions. Any 6 will do. So 10 choose 6. The probability of a success is 25, and each of those successes happens 6 times, which means that 3/4 of the time, well, the probability of not getting a question right is 75%, and you got those questions wrong the remaining 4 out of the 10 times. So 6 plus 4 adds up to our 10. So we can just key this into a calculator and we'll get an answer. After consulting a calculator, we get 0.01622, or in other words, we get 1.6%. Okay, well, that's the probability of getting exactly a 6, but you want to know what's the probability that you pass. So you could pass by getting 7 correct, and it's probably like less likely than the 6, but hey, it's something. So passing, meaning getting a 60% or better, you could do that by getting a probability of 6, or a probability of 7, a probability of 8 out of those 10, probability of 9 out of 10, or oh lordy, you could conceivably, there is a chance, get all 10 of those questions correctly. So if you want to know the probability of passing, these are 1, 2, 3, 4, 5 mutually exclusive events, so we're going to use an addition rule. So we've already done one of these. We did probability of getting 6 right. That was 1.6%. We can just go through these same steps, calculating individually each of these probabilities and then just adding them together. So give me a sec, I'll do it on my calculator, I'll check back. So I've consulted the calculator. Probability that we would get 7 right is smaller, of course, than we would get 6 right. So that is 0.31%. Probability that we would get 8 right is 0.039%. The probability that you would get 9 is 0.000 something percent. Probability of 10 is much, much smaller than that. What's the probability that you would pass? Well, I can add those up, which I did, and we get 1.97%. which, that's not good news. You need to study. So we've seen now how to do this by hand. We've also seen that this is really tedious. And for like a simple 10-question quiz, I was running out of decimal places there when I was doing it by hand. So this is a perfect place to start using Excel to calculate our binomial probabilities. So let's switch over to Excel and see how this is done. Okay, so we'd like to see what's the probability that we would get 6 questions out of our 10. And rather than just keying in the details of the formula, let's try to use Excel's built-in formulas. So all formulas start with an equal sign. This is a binomial distribution question. So binom, and then it starts suggesting, and we need dist. The formula used to be binom dist without the dot in between those two letters, but these formula names started to get really big, so Excel started putting dots in between them to make them look more readable. So we open up our parentheses, and then we get prompted for some more input. The number of successes, that's that number underscore s there, that was 6. But rather than keying in 6, I'm just going to say, that number in cell A1. The number of trials was 10. Probability underscore s, that's the probability of success. We said that was 25%. And now this thing called cumulative. Now, what we're going to want is just the probability. If we wanted the probability that it is a particular number or less than that number, then that's a cumulative probability, because you would be adding up all of those probabilities. That's not what I want right here, at least not yet. So let's just get the plain probability by doing false. Right? So I just want the probability, not the cumulative one. And we hit enter, and we get the same number that we got by hand in the previous screen. Now, I can do the same thing for if I got 7, 8, 9, or 10 questions correctly. And since in my formula I had this, I didn't key in the 6, I had it pointing to a particular cell, then I can just copy that formula all the way down. Right? Just drag and drop, or alternatively, just double click, and it'll copy that formula, and you'll see that it's still putting in the 10 occurrences, 25% probability of success, but for 10, it's pointing to A5 for the number of successes. Oops. So that probability is something that's really, really like small. It's 9.5 times 10 to the negative 7 power. What is the probability that we would get a 6 or a 7 or an 8 or a 9 or a 10? We can just add up all of these. So add up B1 through B5. And that's our probability. We can also express this as a probability by clicking the percent right there and maybe increasing our decimals. And we have a 1.97% chance of passing this test without studying, which is the same number that we had from before. Now, there is an even easier way of answering this question using Excel, and that is by using the cumulative distribution function. So let's see what we mean by that. Now, what I'd like to do is just kind of insert some more cells in here. So we could have gone down to having no answers correct. And let's copy our formula. We can get rid of this guy. Actually, let's leave him up there. So these are all the probabilities from the binomial distribution if we have 10 coin flips, 10 questions that we want to know about. And so one way of getting the 6 or better answer is to add up probabilities of 6, 7, 8, 9, and 10. An alternative way of doing that is by doing 1 minus 0 through 5. So 1 minus all of these. and we get the same number. But what about this cumulative distribution function? So binom dist, the number of successes that we want for passing the quiz, that was 6. The number of trials was 10. Probability of 0.25. This time, let's see what happens when we put true for cumulative. Now we get 0.9964. So near certain that we are going to get less than a particular number. Now, what number do we want less than? We don't want 6 anymore. We want 5. And what we want, so this guy here gives us this probability. What we want is 6 or more, so we need to use our rule of complements and go 1 minus. And now we get our 1.97%. Okay, so the idea, if I can just turn on my equations here real quick, is that I want the probability added for me. So I'm going to use the cumulative distribution function. But a cumulative usually tells you probabilities less than or equal. I want to know if I pass, so I want probabilities greater than or equal. Excel doesn't give me greater than, it gives me less than. So I need to mess with it by using the rule of complements to get the greater than. The only adjustment you have to make is, well, do I need to include 5? Is it or include 6? Now the way that Excel does the binomial distribution is it tells you, like when you're doing the cumulative, probability of less than or equal to something. So less than or equal to 5 includes the 5. 1 minus that is going to give you your 6s through 10s. So that's why we have here 1 minus the cumulative distribution of 0 through 5 with that 5 thing right there. So that's how you do binomial distribution questions using Excel or with pen and paper. Thanks for listening.